In this lecture, we will describe the notion of measure. So far we have learned set function, and we will see that measure is a special class of set function with some conditions. The measure theory developed in 90s and 20th century gradually, and this is some sort of generalization of the concepts that we already have, like length, area, volume, etc. So, once we define measure, the next thing we will be going to describe is the properties. We will describe few of the measures that we commonly use or which are very important to a statistician. Then once we have these things, we will find few of the measures, especially Lebesgue measure of a set and few properties of the measure. I hope this lecture will give a brief introduction to the concept of measure. Let us start with some informal definition of measure. A measure on a set is a systematic way to assign a number to each suitable subset of that set. So, this is a systematic way to assign a number. A measure is a generalization of the concepts of length, area, volume that we all know of this n dimensional Euclidean space R to the power n. So, it is a generalization of the existing concepts. A particularly important example is Lebesgue measure, which is defined on a Euclidean space, which assigns the conventional length, area and volume of Euclidean geometry to suitable subsets. This measure theory was developed in successive stages during the late 19th and early 20th century. Now, we will come to a more formal definition of measure. Now, we are considering a sigma field which consists of the subsets of the reference set omega. We denote it as script f. So, script f is the sigma field of subsets of omega, the reference set. Now, measure is a set function with some restrictions. So, a set function mu defined on this space omega and script f is called a measure if it satisfies the followings. First condition that it has to satisfy is that mu a is greater than equals to 0 for all a belongs to the sigma field. That means measure is non-negative. Second condition that it has to satisfy is that if we are considering a null set, then measure of a null set will be 0. And the third condition, we are satisfying that mu I from 1 to infinity a I. So, I am taking union over countable union over all sets, and the union of these sets will result in a set, and the value of the set function defined on this set will be sum of their individual set function if the sets are mutually disjoint. That means mu of I from 1 to infinity a I will be sum over I from 1 to infinity mu of a I for all a I belongs to the sigma field, and a I intersection a j is phi whenever I is not equals to j. So, a measure is a non-negative sigma additive set function with mu phi is 0. So, non-negative and sigma additive, these are the two very important terms to define a measure, and omega, script f and mu, this triplet together is called measure space. And a measure mu defined on this measurable space omega and script f is called sigma finite if omega, which is exhaustive of all this a1, a2, a3 and countable unions. So, if omega is equals to union over I from 1 to infinity a I and all the measures of each set is finite, then we call mu to be a sigma finite. Now, sigma finite measure is not same as the sigma additivity which we have already known. So, sigma finite measure, we are considering one example to show what do we mean by sigma finite measure. Let us consider the real line R and define the measure as the length of an interval. So, we are considering intervals and we are considering measure as the length of an interval. So, we are considering closed intervals, suppose k to k plus 1 and k are the integers. So, if I take one interval, then the length of this interval will be k plus 1 minus k, that is 1, and in real line there are countably many such intervals, each having the measure 1. So, all these measures are finite, but if you consider the union over k from 1 to infinity, k to k plus 1 will result in the whole real line. So, if I take the measure over the whole real line, it will not be finite. So, this is an example of a measure which is sigma finite, but not finite. Now, we have in mathematics different measures, lot of measures are available, but we will be focusing on counting measure, which will give number of elements in a set, Lebesgue measure, which is very important, which is a measure we define on an interval. Then we have the most important in our case is the probability measure, where every probability space gives rise to a measure called probability measure. Now, consider a few more examples. Now, if I consider the reference set to be the real line and the sigma field as phi, omega, all countable and co-countable subsets of omega, the reference set. This consists my sigma field. Now, I define the set function or measure as 0 if A is countable, 1 if A is co-countable, and mu phi is 0 for obvious reason. Now, suppose A1, A2, A3 they are countable. If they are countable, their union I from 1 to infinity ai, this set, if I define the measure on this set, by definition it is equals to 0, and since each of these A1, A2, A3 they are countable, the measure on each set will also be 0. So, in both the cases what I am getting 0. So, mu union over I from 1 to infinity ai is same as sum over I from 1 to infinity mu of ai. Now, if we assume that at least one is co-countable, if at least one is co-countable, then I from 1 to infinity ai, this set will be co-countable. So, the set function defined on this set, the measure defined on this set will be 1. Many of the sets A1, A2, A3 may be co-countable, since we are considering at least one is co-countable. Whenever they are co-countable, their contribution will be 1. So, if I add them together, the sum may go to infinity. So, the left hand side is 1 and right hand side is infinity. So, this is an example which shows that this is not sigma additive. Now, we consider another example. This is the second example. Let omega be the reference set and script f is the sigma field, and the sigma field is defined as phi, omega, all countable and co-countable subsets of omega, just like the previous example. This is the sigma field. Now, we are defining the measure mu a as the number of elements in A, if A is finite. If A is not finite, then it will be infinity. So, for obvious reason mu phi will be 0, because we do not have any element in phi, and we define measure in that way that null set the measure will be 0. Now, we consider the set A, which consists of the following elements 1, 2, 5 and 8. Then mu A will be 4, because the measure says that how many elements are there in a set. Since there are 4 elements, mu A will be 4. Now, if my set consists of all the numbers like this 3, 5, 7, 9 and so on. So, this is an infinite set, and from the definition of the measure mu, it will be infinity. So, this is another example of measure. This is basically counting measure. Once we define measure and gave few examples, now we want to know what are the properties of measure. The first property that we will be discussing is called monotonicity. That means, if you consider two sets A and B both belonging to the sigma field script f, and one is a subset of other, that means A is a subset of B, then the measure defined on A will be less than equals to the measure we are defining on B. The proof is not very difficult. A is a subset of B, that means there are some elements which belongs to B, but not in A. So, we define the set of those elements as C, and A union C is same as B. So, C are those elements which belongs to B, but not A. Now, if I take the measure, mu A union C will be mu of B, because A union C is B. One thing to be noted, that A and C, they are disjoint. So, if they are disjoint, mu of A union C will be mu A plus mu C. So, mu A plus mu C will be mu B using this additive property. Now, we know measure is non-negative quantity, that means mu of any set is greater than equals to 0. So, if you are taking the measure over the set C, it will be greater than equals to 0. So, this clearly implies that mu A is less than equals to mu B. So, this is the property attributed as monotonicity. The next property that will be discussed is called countable subadditivity. What do you mean by countable subadditivity? Suppose we are considering A1, A2, An and so on, all the sets belonging to this sigma field script f. Then mu of union over I from 1 to infinity Ai is less than equals to sum over I from 1 to infinity mu of Ai. To prove this countable subadditivity, we will reconstruct this union over A1, A2, An through a set B1, B2, Bn and so on. So, we define B1 equals to A1. Now, B2 is defined as A2 intersection A1 complement, B3 is defined as A3 intersection A2 complement intersection A1 complement. So, in general, Bi is defined as Ai intersection A1 complement, A2 complement, A3 complement and Ai minus 1 complement. And if you note that I from 1 to infinity Ai, if I take all the union over Ai is same as taking the union over Bi's. So, the whole exhaustive set Ai is replaced by this set Bi, because if I take the union, they will result in same sets. So, the measure over union over I from 1 to Ai is same as measure if I take union over I from 1 to infinity Bi. Now, the advantage is that if you note that B1, B2, B3, they are all mutually disjoint. If they are disjoint, then their union can be replaced by sum. So, it will be sum over I from 1 to infinity mu of Bi, and by notation Bi is nothing but Ai intersection A1 complement, A2 complement, Ai minus 1 complement. So, this will be mu of Ai intersection A1 complement, A2 complement, Ai minus 1 complement, and this is obviously less than equals to mu of Ai. The reason is that consider two sets, one consists of all the intersections and the other without any intersection. So, if I put more intersections in a set, that means we are putting more restrictions, we are getting lesser number of elements if we increase the number of intersections. For two sets A and B, A intersection B is a subset of A. Similarly, if you have A, B, C three sets, then A intersection B intersection C will also be a subset of A. Using that logic, you will find that Ai intersection Ai minus 1 complement, Ai minus 2 complement and so on A1 complement, this set is a subset of Ai. Now, using the monotonicity, we can claim that mu of the measure on the defined on the intersection set is less than is equals to mu of a I. This completes the proof. So, these are the two properties that are very important for a measure. One is monotonicity, the other one is countable subadditivity. Monotonicity says that if you have two sets, one is a subset of the other, then the measure defined on the superset will be greater than equals to the measure defined on the subset. Similarly, the countable subadditivity says if you take the measure over union over I from 1 to infinity I, countable union of sets, that is less than equals to countable sum of mu of a I, their individual measures. In this lecture, we have learned the definition of measure, properties of measure. We have seen a few examples also. We define what do we mean by sigma finite measure and a few examples too. So, the measure in a nutshell is a generalization of our known concepts of length, volume, area, etc.